Namaste. Welcome to the next video of Machine Learning Techniques course. In this video, we'll discuss loss function of linear regression model. In the last video, towards the end, we looked at this illustration, which shows a loss or error incurred due to a particular choice of a model. The model is represented by a blue line over here, and the training data is represented with these green dots. So we have feature x1 on the x-axis and the corresponding label y on the y-axis. And you can see, for example, this particular value of x1 has value of y. This is the actual value of y. But because we have modeled this training set with the blue line, the predicted value of y is somewhere over here. So the predicted value and the actual value are different, and there is some amount of difference or error between the predicted value and the actual value. So the loss function essentially helps us capture this error across the training set, across points in the training set. So linear regression uses a specific loss function known as sum of squared error. Sum of squared error, as the name suggests, is the sum of square of difference between the actual value and the predicted value of the output for each training point. We can write it as the square of difference between the predicted label and actual label at every training point, and then we sum it over across all n training examples. And that is sum of squared error for us. Let's look at the error at I training point. So the error at I training point is denoted by E superscript I, and it is defined as again the difference between the predicted label and actual label, and we square up the difference. So that is the error at I training point. And the predicted label is obtained with the model, right? So we use a feature vector for I training example, which is denoted by xi. So we take this feature vector, we pass it to the model, and we obtain the predicted label. In case of linear regression, since we take linear combination of the features, we have a particular functional form which is W transpose xi, where W is the weight vector of the model, x is a feature vector, and yi is the actual label. So W transpose xi gives us the predicted label for ith example, and we take the difference of this predicted label with the actual label, we square up the difference. So that is the error at I training point. Since we square up the difference, the error is a non-negative quantity, or in other words, the error is always greater than or equal to 0. The error is equal to 0 whenever predicted label and actual label are identical. So when that happens, the error is equal to 0. So the total loss JW is sum of errors at each training point. So JW is sum of error across all n training examples. So we add or we divide this particular error by a factor of half for mathematical convenience in later case. So by applying the factor of half, we get JW is equal to half of the sum of errors at each point in the training set. And this error is calculated as the square of difference between the predicted value and the actual value at each training example. So you can see that the loss is actually dependent on W. So the loss, in other words, is function of W, that is the weight vector. You can see that as you change the weight vector, we get a new model, and because of that, we get a new prediction. And due to this new prediction, we might get a different error at each training point. And when we sum across all training points, we will get possibly a different loss. So hence, the loss is the function of weight vector. Got it? And other way to look at it is the value of xi and yi is going to be constant because we fix the training set before launching the training pipeline. So only thing that is changing is the weight vector, and hence the loss function is function of the weight vector. We can vectorize the sum of squared error for efficient computation. We know that the SSE is denoted by JW, which is sum of square of difference between the predicted value and the actual value. We know that the prediction, we can get the prediction for all points by multiplying the feature matrix with the weight vector. So we'll use this particular formula in this particular formula in order to obtain the vectorization of the loss function. So what we do is we substitute xw to w transpose xi. So w transpose xi essentially gets us a label for a single example. But when we perform the matrix vector multiplication of the feature matrix and the weight vector, we obtain labels for all example at once. And this is the label vector, this is the actual label vector. It contains the actual values of the output. So we take the difference between the predicted value and actual value, we take the transpose of it and multiply it with the same quantity, with the difference. So this particular quantity you can perform the maths and check that this is indeed equivalent to this particular quantity. So what we'll do now is, now that we have the vectorized implementation, we will implement it in a Python function. So the loss takes three arguments: features, labels, and weights. So we initially compute the error vector, which is the predicted value minus the actual value, and then we perform this particular matrix operation. Okay, so we first transpose the error vector that we obtain here, and we perform a matrix multiplication with the error vector, and then we multiply it by half in order to compute the loss, and this function returns the loss value. Got it? So let us visualize the loss function. Let's see how this loss function looks like. So in order to visualize the loss function, we'll select a simple model containing a single feature. So our model is y is equal to w0 plus w1 x1. It has got two parameters or two weights, which are w0 and w1. So the corresponding sum of squared error loss function can be written by substituting the value of the model, and that is half sum over all training examples. The predicted value can be obtained by the model formula or by the model, which is w0 plus w1 x1. Of course, we perform this operation on IIT training example. This gets us the prediction for the IIT training example, and we subtract that from the actual label and we square up the difference, and then we of course sum across all an example, multiplied by half to obtain the total loss. And in the last slide we saw that this loss function is actually a function of weight vector. So in this case, weight vector has two components, W0 and W1. So now what we'll do is we'll vary the values of W0 and W1, and for each combination of W0 and W1 we'll obtain a weight vector, obviously by fixing the training set, because once we fix the training set we have fixed values of features and labels, and by just varying the values of W0 and W1 we will be able to obtain the corresponding loss for the pair of W0 and W1. So we now plot the triplet, that is the pair, the values of W0, W1 and the loss value. So you see that W0 is on one axis and W1 is on another axis. The third axis is actually the loss. So for a pair of W0 and W1, we actually obtain a value of a loss. So this is a loss landscape or loss surface, and this surface is a bowl-shaped surface. And a good property of this surface is that it has got a single minima, right? A single minima which corresponds to the value of W0 and W1 such that the loss is the least among all the values. That is the minima, and that is the desirable point, right? Because at that point the loss is minimum, and that is probably the model which is likely to perform well also on the unseen data. It will definitely perform well on the training data because we are training it on that, but it is also likely to perform well on the unseen data. Apart from that, you can also see a bunch of concentric circles in W0, W1 plane. That is an alternative representation of this loss landscape, and this representation is called as a contour representation. So the innermost concentric circle has the lowest loss, and as we move away from this particular center, we get circles that represent higher and higher losses. So these concepts will be a bit more clearer in the next slide, where we'll actually be able to interact with the loss landscape. So now that you are familiar with the loss landscape or loss surface, let's try to understand the concept of duality between loss and model spaces. So here you see a visualization with two different frames. The left frame has got a visualization of the loss surface, whereas on the right frame we have a place to show the model and the training data that is used for computing the loss. A single blue point is an instance of a training data, and these are a bunch of blue points. They represent what is called as a training set. The training set has obviously a feature and a label, and we are considering a very simple model here, again as usual, a model containing a single feature x1, and we have a linear regression model which calculates the output label y by linear combination of the features. So in this case y is equal to w0 plus w1 x1, and the line that you see over here is the current model. And there are three numbers that you see over here. These three numbers denote, the first number denotes W0, this is the value for W0. The second number is the value of W1, and the third number is the value of the loss. On the left hand side, we have a loss surface. So it has got three axes, one corresponding to W0, second corresponding to W1, and then this vertical axis corresponds to loss. So again, as we discussed in the previous slide, we got this particular loss surface by sampling many pairs of W0 and W1 and computing losses for them, and then we plotted that loss for the pair of W0 and W1. Now, the point that I want to demonstrate on this slide is the duality of the loss and model spaces. So before that, we will click on this button for showing the contours. So this draws the contour, which is another alternative representation for the loss surface. Now what we will do is, we will try to, so current model is a point on the loss surface, which is denoted by this particular yellow ball, right? This yellow ball is the current instance of the model. This yellow ball is currently situated at W0 equal to minus 0.25, W1 is equal to minus 3.11, and it has got loss of 1.1. Now what we'll do is we'll slide this yellow ball, and you can see that as we slide this yellow ball, we see this particular line changing, right? And at the same time, we see different values that are appearing over here. So again, those are the values, as I earlier said. This is the value of W0, this is the value of W1, and this is the value of the loss. So as I keep sliding this particular yellow ball, or as I start taking different positions on the loss surface, I get different models, right? So as I move closer towards the minimum point, which is somewhere over here, or the bottommost part of this loss surface, I get almost perfect model, right, which has got error of 0. You can see that this is the model with error of 0, and this is the bottommost part, or this is the bottom of the loss surface or of the bowl that we see over here, right? And as we move away from this particular bowl, you can see that this particular ball, so you can also see the projection of this ball on the contour. It is right at the center of this concentric circle. So that is the point where we have the least loss, and the values of W1, W0 and W1, or the values of the weight vector that corresponds to the optimal model, the model that obtains the least amount of error among all other models. As we slide this particular ball away from the center, you can see that the error starts increasing, right? And the model fitment is becoming worse and worse. Right? You can see that we are moving away from the training set, the error is also going up, right? And as I come closer to the center, I have better fitment, right? So we can see that the point closer to the bottom gets us better fitment than other points that are away from this particular bottom, right? As we go, let's say over here, we get model that has got a very poor fitment. Got it? So I would strongly recommend you to play with this visualization. This will help you to get more clarity about duality between loss and model spaces. And this is a very important concept. You should remember this, that a model is merely a point on the loss surface, right? And as we traverse to the loss surface, each instance where we stop on the loss surface gets us a new model, right? And we'll be using these concepts in optimization, right, which we are going to study next. So for the takeaway message from this particular visualization is that the model is a point on the loss surface, and as we move in the loss surface, the loss changes as well as the point changes, right? And the loss is least, we obtain least loss when we move closer to the bottom of this particular bowl shaped surface. Got it? So, this is fine. We can actually do this visually and we can control where we are, and we can obtain this nice visualization because we are uh, really, showing this for a toy problem with a single feature. But in real world, we have, data sets with many different features, and such a visualization is simply not possible. So in that case, how do we really find out the optimal point in the loss surface? That's the central question in training, and we will study that question in our next component, which is the optimization component. So hope you like this particular visualization, and you got to know better about the concepts of loss function in linear regression. In the next video, we'll study the optimization component of linear regression model in detail.